Aerodynamics. A subfield of fluid dynamics, aerodynamics studies the physics of a body moving through the air. As lift and drag are functions of airspeed, their relationships are major determinants of an aircraft's design efficiency. Aircraft efficiency is augmented by maximizing lift-to-drag ratio, which is attained by minimizing parasitic drag and lift-generated induced drag, the two components of aerodynamic drag. As parasitic drag increases and induced drag decreases with speed, there is an optimum speed where the sum of both is minimal. This is the best glide ratio. For powered aircraft, the optimum glide ratio has to be balanced with thrust efficiency. Induced drag can be reduced by decreasing the size of the airframe, fuel, and payload weight, and by increasing the wing aspect ratio or by using wingtip devices at the cost of increased structure weight. Design speed. By increasing efficiency, a lower cruise speed augments the range and reduces the environmental impact of aviation. However, a higher cruise speed allows more revenue passenger miles flown per day. Wingtip devices. These increase the effective wing aspect ratio, lowering lift-induced drag caused by wingtip vortices and improving the lift-to-drag ratio without increasing the wingspan. Weight. As the weight indirectly generates lift-induced drag, its minimization leads to better aircraft efficiency. For a given payload, a lighter airframe generates a lower drag. Minimizing weight can be achieved through the airframe's configuration, materials science, and construction methods. To obtain a longer range, a large fuel fraction of the maximum takeoff weight is needed, adversely affecting efficiency. The dead weight of the airframe and fuel is non-payload that must be lifted to altitude and kept aloft, contributing to fuel consumption. A reduction in airframe weight enables the use of smaller, lighter engines. The weight savings in both allow for a lighter fuel load for a given range and payload. A rule of thumb is that a reduction in fuel consumption of about 0.75% results from each 1% reduction in weight. The payload fraction of modern twin-aisle aircraft is 18.4% to 20.8% of their maximum takeoff weight, while single-aisle airliners are between 24.9% and 27.7%. An aircraft weight can be reduced with lightweight materials such as titanium, carbon fiber, and other composite plastics, if the expense can be recouped over the aircraft's lifetime. Fuel efficiency gains reduce the fuel carried, reducing the takeoff weight for a positive feedback. For example, the Airbus A350 design includes a majority of lightweight composite materials. The Boeing 787 Dreamliner was the first airliner with a mostly composite airframe. Flight distance. For long-haul flights, the airplane needs to carry additional fuel, leading to higher fuel consumption. Above a certain distance, it becomes more fuel efficient to make a halfway stop to refuel, despite the energy losses in descent and climb. For example, a Boeing 777-300 reaches that point at 3,000 nautical miles. It is more fuel efficient to make a non-stop flight at less than this distance, and to make a stop when covering a greater total distance. Very long non-stop passenger flights suffer from the weight penalty of the extra fuel required, which means limiting the number of available seats to compensate. For such flights, the critical fiscal factor is the quantity of fuel burned per seat nautical mile. For these reasons, the world's longest commercial flights were cancelled. An example is Singapore Airlines' former New York to Singapore flight, which could carry only 100 passengers, all business class, on the 10,300-mile flight. According to an industry analyst, it was pretty much a fuel tanker in the air. Singapore Airlines flights 21 and 22 were relaunched in 2018 with more seats in an Airbus A350-900 ULR. Propulsive efficiency. The efficiency can be defined as the amount of energy imparted to the plane per unit of energy in the fuel. The rate at which energy is imparted equals thrust multiplied by airspeed. To get thrust, An aircraft engine is either a shaft engine. Propulsive efficiency. The efficiency can be defined as the amount of energy imparted to the plane per unit of energy in the fuel. The rate at which energy is imparted equals thrust multiplied by airspeed. To get thrust, an aircraft engine is either a shaft engine, piston engine, or turboprop, with this efficiency inversely proportional to its brake-specific fuel consumption, coupled with a propeller having its own propulsive efficiency, or a jet engine with its efficiency given by its airspeed divided by the thrust, specific fuel consumption, and the specific energy of the fuel. Jet fuel cost and emissions reduction have renewed interest in the prop fin concept for jetliners, with an emphasis on engine airframe efficiency that might come into service beyond the Boeing 787 and Airbus 350. For an instance, Airbus has patented aircraft designs with twin rear-mounted counter-rotating prop fans. Prop fans are a more fuel-efficient technology than jet engines or turboprops. Altitude. Air density decreases with altitude, therefore lowering drag. Assuming the aircraft maintains a constant equivalent airspeed, this means an aircraft may be more efficient at higher altitude. With increasing altitude, air pressure and temperature both decrease, causing the maximum power or thrust of aircraft engines to reduce. In a piston engine, this trend towards a decline in maximum power can be mitigated by the installation of a turbocharger. Decreasing air temperature with altitude increases thermal efficiency.